So hi everyone, my name is Virginia Detti, with a team on increasing the efficiency of sequential decision-making algorithms and specifically Bayesian optimization with leveraging LLMs and FunSearch. So I believe you had quite a few talks on Bayesian as part of this seminar, so I'll just give you a brief introduction on the topic to set a bit the ground of what I'm going to be talking about in the talk. So Bayesian optimization is part of a broad set of algorithms that can be used to solve black box optimization problems. And in Bayesian optimization, you're given a function, f of x, and you're interested in finding the optimum, x star. However, the function is explicitly unknown, might be multimodal, perturbed by noise, gradients are not available, and so the only thing that you can do to learn about the function is to actually query it. However, evaluations might be expensive or limited depending on the application that you're looking at. So this problem emerges in different areas. So Bayesian has been used extensively for hyperparameter optimization. So for example, for selecting data mixtures in LLMs. It has been used for robotics. It has been used for drug design. And something that I worked on a lot in the past was using Bayesian for selection of optimal policies in causal environments, so causal decision making. So Bayesian finds the optimum by sequentially collecting a number of function evaluations, also called trials, and turning the original optimization problem into a sequence of decision problem of where to select, where to collect the next function evaluation. So in Bayesian, there are two main ingredients generally for the majority of Bayesian algorithms. There are a surrogate model and an acquisition function. So the surrogate model that you see on the top plot here captures the our belief about the objective function, and it gets updated as we collect more data and we get more observation about our function. So this can be a Gaussian process, as is done here, but it could also be a Bayesian neural net, a transformer. And the second ingredient of most of Bayesian algorithms, which will be the focus of this talk, is the acquisition function. So the acquisition function, and you see one example here on the bottom plot, is also called the sampling policy, or the function that determines, based on the parameter of the surrogate model, where and potentially hyperparameters, where to collect the next point. And so one common acquisition function is the expected improvement, which, starting from the GP hyperparameters, compute the probability of observing a better value on the input space. So at every step of the optimization problem, and the next function evaluation is found by optimizing numerically the acquisition function. So in this case, this optimization leads to the point that is marked by the red dashed line. And so evaluating the function at that specific point that we selected will lead to a lower observed function value you see on the top with the denoted by the red arrow, and so given this would lead to an update of the GP model parameters, and the computation of the acquisition function will be again updated. So we'll have a new expected improvement, and we will continue to repeat this step. So this will drive the algorithm to collect points in different areas of the input space, and we'll have this loop of finding the next point to evaluate, collecting the data point, updating the point that we use to update the GP, and then until we achieve a specific stopping criteria. This could be, for example, a maximum number of trials. And at that point, the best point among the collected point is returned. So it should be clear at this point that the acquisition function plays an important role in determining the efficiency of Bayesian optimization algorithm, but also other algorithms such as active learning algorithms or Bayesian experimental design methods. So the acquisition function, all acquisition functions generally balance exploration and exploitation, determining, contributing to determine the number of trials that we need to collect before finding the true optimum. So different types of acquisition function have been considered in the literature, and we can generally group them in two main sets, or at least that's how I think about it. On the one hand, we have acquisition function that aim to provide general purpose optimization strategy. And on the other hand, we have approaches that are tailored to specific function types. So in the first set, you find expected improvement, UCB, probability of improvement, so widely adopted general purpose acquisition function that we can use out of the box across optimization problems. Part of this, included in this class are also more complex, for example, entropy-based acquisition functions that are, though, expensive to evaluate and generally require some approximation. Several studies have tried to go beyond this general purpose acquisition function and use transfer learning methods to find acquisition functions that are specialized to a specific class of function. So generally, these acquisition functions outperform general purpose one, but their generalization performance to objectives that are outside of the training distribution might be poor. So we're thus interested in understanding whether we can develop a methodology that can automatically identify new, well-performing acquisition functions that are capable of outperforming, depending on how they're trained, general purpose acquisition function or function-specific alternative. And specifically, we ask a set of questions that will sort of motivate this talk. So is it possible to leverage LLMs to find well-performing acquisition functions? So we'll use well-performing acquisition functions to speak about acquisition functions that, when are used within a Bayesian algorithm, perform well across a number of optimization problems. And if yes, can we use LLMs to also meta-learn acquisition function for, say, finding acquisition functions that perform well in hyperparameter optimization problem or few-shot adaptation problems? And also, what is like as this acquisition function generalizing well, and what about in distribution or out of distribution? So to answer these questions, we used FunSearch. Now, FunSearch is a recently proposed evolutionary algorithm for searching in the functional space by combining an LLM that generates new computer programs with an evaluator that scores these programs. And so it guards against hallucination. So I'm just going to give you a bit of an overview on FunSearch and then talk a bit about how we, sort of instantiated FunBayes to solve the original problem of learning acquisition function. So FunSearch considers an initial problem that is here that depends on a specific heuristic or a program. For example, one of the problems that they consider is the bean packing problem, where you have items that are arriving online and of a specific size, and you have to assign them to beans, with the idea of minimizing the number of beans that are used. And so FunSearch has, prompt the LLM with an initial commonly used heuristic or program, for example, first fit, which is like assign the item to the first available bin, and then ask it to generate functions or programs that improves on existing heuristics. It then scores this program based on how well they solved the original problem, and then stores them in a program database from which we can then sample successive prompt to then re-prompt the LLM and then do multiple iteration of this loop. So the procedure repeats for a certain number of iterations, and the best program found is then returned. So this is a bit FunSearch. Now, in our work, we view the problem of learning new acquisition functions as an algorithm discovery problem in computer code, so in the program space, and propose this algorithm, which is FunBayes, which builds on top of FunSearch and combines it with Bayes, focusing, as I mentioned just now, on acquisition functions that are written in computer code. So FunBayes follows the same structure of FunSearch. However, FunBayes prompts the LLM with a given, acquisition functions that is generally used across optimization problem, for example, expected improvement, and then prompts it to generate computer programs that is better or outperforms the current one. The better is again defined with respect to scoring mechanism, and so the generated acquisition functions are scored based on a metrics that measures how well such an acquisition function solves the problems, a specific optimization problem. So given the scores, the acquisition function are then stored in the program database, And so there's an island model that basically is underpinning this program database. And this process is repeated multiple times until the best performing acquisition function on a set of new objectives is returned. Now, I'll go a bit more in detail on how we prompt the LLM and which initial acquisition function we use, as well as which scoring mechanism we adopted. So before doing that, note that in this work, we worked with Python to generate computer programs. So all functions and prompts that you see here are in Python. However, FunBO can be applied to other languages that are supported by FunSearch, for example, C++. So the prompt that we use in FunBO is given in this figure here. And you see how the LLM is, first of all, prompted with a description of the problem that we are trying to solve. So this is improved Bayesian optimization by discovering new acquisition function, as well as two acquisition functions that are denoted by V0 and V1. So these are acquisition functions that were previously generated by the LLM and are sampled from the program database. So as in FunSearch, we use two acquisition functions in the prompt, or two programs, and we order these acquisition functions in increasing with respect to the score with increasing order. So we then add the signature of a third acquisition function, which is V2, that the LLM is asked to produce. Note that at the first iteration of the algorithm, the LLM will not have stored acquisition function in the program database, and the only available one will be the initial one that we provide the algorithm with. And so an important aspect of the algorithm is how we initialize this acquisition function. So in this work, we decided to have the initial acquisition function to be the one that you see on the top, which takes the form of the expected improvement and has parameters that are those used by commonly used acquisition functions. So expected improvement, UCB, probability of improvement. So this is in the first iteration of the algorithm, this initial acquisition function will be representing the V0 function. And so all the subsequent generation of the LLM will be both in terms of args that will be used in the acquisition function, and which form will take will be conditioned on this initial one. So this initial acquisition function, you can think about it as a prior, and that sort of like set a starting point for the LLM to explore the function space. One important aspect of the prompt is also the function docstring, which is given in the acquisition function V0, and corresponds to the text that I put here. So you can see how the docstring gives an explanation of what this function is supposed to do, as well as what is supposed to return and the args that are used together with their shape. So this gives a bit of a intuition to the algorithm about what it is supposed to generate. So another important aspect of FunBO is the scoring mechanism. So the scoring mechanism is used to assess the generated acquisition functions. And in general, we found that FunBO needs a scoring mechanism that captures small improvements in the proposed acquisition function, because this is going to steer the LLM towards promising region of the function space, which is a very complex function space. So in this work, we decided to use a score that is composed of two different parts. One that captures how close is the recovered optimum to the ground truth optimum, and then one that captures how fast is the true optimum recovered over the trials. So you can think about the first part capturing how accurate is the optimization when using generated acquisition function, while the second one measures how efficient is the optimization process, again, when using a specific generated function. So higher score means that using the suggested acquisition function led basically to an identification of the true optimum that was pretty fast and within a certain percentage of the number of trials that are available. Obviously, these two elements can be combined in different ways and can be weighted in different ways depending on the specific problem at hand. But in this work, we kept these two weighted in the same way. And we tried different alternatives. For example, we tried a binary score, giving 1 or 0 based on whether the algorithm using an acquisition function was converging or not. But we found this not to provide enough signal or guidance to the LLM in terms of exploring the function space. We also tried to use the negative cumulative regret, but we found that this was giving pretty equivalent results to the metric that then we ended up using. Okay, so now putting all of these pieces together, so the scoring mechanism, the initialization of the acquisition function, the prompting, we can look at the full Bayes-Opt algorithm altogether. So FunBO takes an initial acquisition function, which here is denoted by this H, and a problem definition, which is E. And this problem definition is again another Python program that executes or deploys a specific acquisition function within a Bayes-Opt loop. More importantly, I think FunBO takes two sets of functions as inputs. So one is used to train the algorithm to find good acquisition function, and the other one acts as a validation set. So given the initial acquisition functions, the LLM is prompted to generate a set of improved version of the acquisition function, and these are represented by the blue boxes. These are then scored, are scored based on the scoring mechanism that I just described. The scores, the functions together with their scores are then added to the program database. Now, the program database is unchanged with respect to what was done in FunSearch, but for completeness, I'm just going to mention that the database keeps a population of corrected programs following an island model. And so the database is initialized with a number of islands that are evolving independently. And so at the start, all these islands are initialized with the initial acquisition functions that I described before. And so every time that we have to create a new prompt, 2 functions are sampled from the program database. So we first uniformly sample the island, and then within the island, functions are organized in clusters based on their score. And so we first sample the cluster favoring functions that are higher scoring, and then within that we sample programs favoring programs that are shorter. When a new program is generated using 2 functions sampled from the same, from a specific island, the functions that is generated is going to be added to the same island with the score, to a cluster that reflects the score that the function achieves on the training function. So this evolutionary procedure is used to encourage diversity. And so once the iteration of tau, in this case, we set up a time budget as a stopping criteria. We select functions, we select the acquisition function that is stored in the database and achieves the maximum score on a second set of function, which adds as a validation set. And then finally, these acquisition functions that were selected on the validation sets are then used to optimize function in a third set, which is the test set. So you have this training set that is used to explore the function space. You have this validation set, which is again a set of functions used to select the best performing acquisition function from the program database. And then you have a third set that is just a test set on which the acquisition function is used. Now, the way in which these training, validation, and test functions that are defined depends on the question that we want to answer. So in this, work, we had some questions at the beginning, and we have different type of experiments that match the questions that we want to answer, basically. So the first experiment focuses on the generalization of these found acquisition functions out of distribution. And so it focuses on investigating whether FunBO can be used to learn acquisition functions that are general purpose and that can be used across optimization problems. So in this experiment, what we did was to train and validate and test the generated FunBO with completely different standard global optimization benchmarks. And because the generated function is akin to general purpose acquisition function, we compare against expected improvement, UCB, probability of improvement, and the mean has an acquisition function, mean of the GP. In the second experiment, we tested generalization in distribution. And so we investigated whether FunBO can be used to generate acquisition functions that are specialized to a specific set of optimization problems. And to do that, we trained, validated, and tested on different instances of the same function obtained by scaling and translating the same function. So this setting is closer to a meta-learning setting. And so for this experiment, we compared, again, standard acquisition function, but also meta-based opt, which is a meta-learning approach, learning an acquisition functions that is parameterized by a neural network via a proximal policy algorithm optimization. Sorry. Now, in the third experiment, we finally tested the possibility of using FunBO opt as a few-shot method, as a few-shot learning method, by taking an acquisition function that was previously discovered by training in a large variety of functions, and then tuning it on a very small number of instances from a specific target class. And we compare, in this case, a generated acquisition function against standard acquisition function, and also the acquisition function that is found in this paper, this FSAF, which is an acquisition function trained on Gaussian processes, on a set of functions sampled from a Gaussian process and adapted via an RL-based algorithm. So we ran all experiments with Code, which is an LLM fine-tuned on a large code corpus and based on the Palm model family. This is also the LLM that was used originally in FunSearch. And so what I'm going to do now is show you across all settings plots where you can see the average regret that is achieved by a Bayes-Opt algorithm when using all of these different acquisition functions over the number of trials or function evaluation. Okay, so starting with the first experiment. So for the first out of distribution type of experiment, we included, as I was mentioning, in the training function, 3 different global optimization benchmarks. So you see here Hackley, Levi, Schwefel. And we then validated on one function, one YD function, and tested on a large variety of, again, global optimization benchmark that you see here. And you can see from the table that I put here on the bottom that all these functions that are used to train and test and validate are very different in terms of scale, in terms of input ranges and dimensionality. So we don't do any, pre-processing of these functions before training or testing the algorithm. But despite this, you can see from the plot on the left that then when using the generated acquisition function, this is the blue line, the Bayes-Opt algorithm converges to a zero regret faster than the alternative. And so you can think about FunBO-Opt, in this case, discovering a function that is akin to general purpose acquisition function that we can use across optimization problems. So one nice feature of FunBO-Opt is also the fact that we can actually inspect the acquisition function that are found because they're given in computer code, and we can try and understand why is it that it gives an advantage over other acquisition functions. So you can see here the acquisition functions that we found in this experiment on the bottom plot, left plot, and by inspecting the function, you realize that this is actually a combination of 2 existing acquisition functions that are the UCB and expected improvement. And so the reason why in some cases it performs really well and leads to better optimization results is that it has a more exploratory behavior. And this works well for the optimization of functions with many local minima. So to make this a bit more concrete, if we look at the exploration path, that is the sequence of input values of X values that are selected over trial for 2 functions. You can see that for objective functions that are smooth, for example, the one on the top, the exploration path for Bayes-Opt when using the acquisition function found by FunBO-Opt, as well as when using expected improvement UCB, are all very similar. and so they converge. So they converge very quickly to the global optimum, and then they are basically stuck there. When instead the objective function has a lot of local minima, has in the function on the bottom, both expected improvement and UCB are stuck after a few trials, while FunBO keeps on exploring the search space, eventually converging to the global optimum. And so you can see here how the convergence path for all acquisition functions differ, and the only one that aligns with the red vertical line, which signals the true optimum, is actually the blue one, representing FunBO. Okay, next we look at the second experiment, which is performance within function classes or in distribution. So in this plot, you see the performance for 3 frequently used global optimization benchmarks. And for all these 3 cases, we trained the algorithm with 20 scaled and translated instances of the same function. We validated them on 5 instances and tested on other 100. And you can see how FunBO discovers acquisition function that performs pretty well compared to meta-learned alternative, and also outperform more general purpose acquisition functions. So they achieved its goal of being like function specific. The same can be said for hyperparameter optimization settings. So what we did in the case for the left plot is we try to find an acquisition function that performs well in the optimization of the parameters of ad-hoc. And so we included in this case in the training set the losses for an ad-hoc model on 30 different data sets. We validated on 5 different data sets and tested on other 15. And so once again, you can see here how the acquisition that is identified by FunBO leads to an identification of the optimum that is faster than function-specific acquisition functions that are parameterized by neural nets, as the one found by methodologies. We also look at generalization within set of functions that are sampled from GPs. And so in this case, what we did was to train the model, so to train FunBO with functions that are sampled from a 3-dimensional GP prior with an RDF kernel. And then we tested on GP, so some functions that are sampled from a GP prior with the same kernel, but 4-dimensional. So in this case, there is less structure to be shared across set of functions. And indeed, even methodologies, so if you look at the black line, you notice that even methodologies performs worse than general purpose acquisition function. So the hope, generally, what you hope is to recover general purpose acquisition function behavior. However, in this case, we see that FunBO is able to find an acquisition function that seems to get the best of both worlds. So it slightly outperforms general purpose acquisition function and outperforms methodologies, which is like the closest comparison in terms of meta learning approaches. As a last experiment, what we did was to get the function that we found by training on 20 functions sampled from a GP. So we get this acquisition function that is the blue line. And then what we did was to adapt it with 5 instances of a target class. So in this plot here, you see in green the performance of the function that we just saw for the GP experiment, but just tested on 5 instances opacally. And then in blue, you see the performance of a Bayesian algorithm when using the acquisition function that has been obtained by adapting the green one through 5 shots. And you see here how, again, the acquisition function is improving. So with only 5 shots, the acquisition function goes from the green line to the blue line, and is also, outperforming general purpose acquisition function as expected, but also other few shot adaptation alternatives in which the acquisition function is parameterized by a neural net and is learned via an RL algorithm. Okay, so I would like to now go back to the original questions that we said at the beginning of this talk. And so in general, what we found is that Using FunBase-opt, so this is supported by experiment 1, 2, and 3. So using FunBase-opt, we were able to discover well-performing acquisition functions that are written in computer code that seems to perform well across a variety of optimization problems. The second experiment also showed us that FunBase-opt can be used to identify acquisition functions that perform really well in hyperparameter optimization problems. The first and second experiments also show us that it's possible to achieve performance that are comparable to both learn acquisition function and general purpose acquisition function. And finally, the third experiment showed us that FunBase-opt can also quickly adapt an acquisition function based on the instances, like few instances of a target function. Now, this is all good. FunBase-opt gave good optimization performances, but the current formulation still has many limitations, and I'm going to give you some here. So first, you might have noticed that it requires running a full Bayes-opt loop for evaluating every sampled acquisition function on multiple objectives. This can be costly, especially when using Gaussian processes, and it might not be scalable if we want to use the algorithm as a meta-learning algorithm where a lot of different functions are given in the training set. Second, the scoring mechanism is very simple, and so more research needs to be done to understand if there's a better way of characterizing the convergence path for different acquisition functions. Thirdly, FunBase-opt has a high experimental cost, so it requires obtaining a large number of high quality sample from an LLM, and so this might not always be feasible. Finally, there's also a large variance in the results that we obtain over different runs, and this is due to the randomness both in the LLM sampling and in the evolutionary procedure, and this is also something that was observed in the original FunSearch work. Despite this limitation, there are a lot of possible extensions, and I'm listing here some that I think are pretty exciting. And so the current framework can be used to discover acquisition functions across a wide range of optimization problems. So while here we focus on basic Bayes-opt with the Gaussian process and standard setting, it would be nice to understand how this can be adapted to find policies that are useful for constraint problems or non-myopic optimizations or active learning algorithm or even bandits. It would also be interesting to understand how and what assumption can be encoded in the acquisition function based on the application and also the desired program characteristics. And finally, it would also, and this is something links back to my previous work, and some of you might be interested in that. This approach can also be extended to select, action in a causal setting. And so in that case, it's interesting to understand how one can encode prior assumption or about the causal environment in the acquisition function, and how, having an LLM that has some prior causal knowledge can help in the selection of the right policy. I'm gonna conclude with this. Thank you very much for your attention. Here you find the QR code to find the paper, and feel free to get in touch if you're interested in learning more about this work.